Is it 2018 already? Postdoc, the New Orleans ACS meeting is coming up. I need data. Again. Yeah, I got a little bit of data to present, but I really need some new equipment. New equipment. Well, time to make it rain.
Damn. Yeah. Yeah. Yeah.
Woo! Nice. This is awesome. You have no excuses now.
Yeah. Yeah.
All right. I think we are live on YouTube. Welcome everyone who's joining us. Thank you for those who are watching our live stream today. My colleague Alex is not here, so it'll just be me hosting today by myself. So I hope if there are anybody who have any questions here, I'll do my best to answer them. And welcome everyone. If you're watching live or you're watching the replay of this event, welcome to another episode of Ask Us Anything About Electrochemistry. I'm your host, Dr. Neil Spinner. And as I said, my colleague Alex Peroff is out today, but I'm excited to be here with you. And so the goal of this event here is just sort of to be almost like an office hours kind of a thing. So I'm just going to be here as a resource to answer questions about electrochemistry. I can also go through some questions where there's been in the past about various things we've received on webinars or YouTube videos or other sorts of media like that. And just a few things to mention here before I get started is that you can put all of your questions directly into the chat whenever you like, and then I will address them in the order that they come in. And if you're watching this after the fact, please note that there will be stamps in the description, and you can also post a question as a comment on the video on YouTube if you'd like to have those answered then. There's also about a 20-second delay or so between what I'm saying right now and when you will hear it watching. So keep in mind that when you type your question, there's a bit of a delay here. I also just want to give a shout out to our YouTube channel members. Thank you very much. We really appreciate you joining. And for those who are thinking about becoming members or aren't sure what we have offers there is a join button, and you can see a short video that my colleague Alex made that shows some of the things that we offer there, including a lot of other previous webinars that I've done. For example, a lot of the webinar content and their full recordings are in the members, tier 2 members section of our YouTube channel. So we encourage you to take a look at that if you would like to view some of those content there. I just wanted to say that we also are really well aware that electrochemistry is difficult. So during this session, if anybody has a question and you think it's a difficult question or something, I'll certainly do my best to answer. And we just want to kind of stress that there's no stupid questions. It's electrochemistry, so it is tricky. And I don't want, that's the point of this, is to try to give people the opportunity to ask questions that, maybe you wouldn't be, willing to ask in another form. I'll certainly do my best to answer and, have no judgment, so to speak. And then apologies in advance if I mispronounce anybody's name. It's quite likely. I'll do my best. So again, thanks everyone for joining. And I do see there's a question already. So Let's see. Shazad says, what's the difference between CV, LSV, and SWV, and how are all of them helpful in identifying and doing analysis? So that's a great question, actually. Let me pull up a few things while I sort of start answering your question. I think I'll be able to pull up like the waveforms and kind of describe them, and I can draw a few things as well. I want to see, I think probably can show the waveform. Square wave is the one that has the most interesting, say somewhat unique waveform compared to LSV and CV. Okay, so I've got this up. So let me share with you my screen, and I'll kind of annotate and draw this out for you. So bear with me while I get everything kind of ready here. All right. So, all right. So the difference between CV and LSV is actually pretty simple. There isn't much difference. One of them is basically a subset of the other. So CV, so that stands for cyclic voltammetry. If I can spell properly, which I think I did, that's an O. All right, so cyclic voltammetry, right? LSV is linear sweep voltammetry. Alex always uses the typing thing, and after having just written all of these words out, I deeply regret not also using the typing thing. So I'm going to try to use that next time, the text thing, because my handwriting is bad when I'm not using a mouse on a computer. So it looks even worse right here. So anyway, LSV in the most simple case, okay, so we'll do an LSV. If we consider a plot of time, right, seconds usually, and potential volts, right? What we're doing is we're just from time equals 0, we start somewhere and we move to somewhere else. That's it. So that's an LSV. I mean, it's literally that simple. It's linear sweep. So linear meaning line, right? It's a linear pattern, right? I'm not sweeping in some sort of funky, interesting pattern. I'm sweeping at a scan rate, and so scan rate usually uses the variable nu, and that would be, you know, however many millivolts per second or volts per second, right? It's how fast I'm moving my potential, and I'm changing it at that rate. And so basically that rate is, you know, the rise over the run, right? That's the slope of this curve, okay? The difference between LSV and CV just involves any more than one such sweep, okay? So the difference between LSV and CV is simply LSV is 1 and CV is when you do, C stands for cyclic. So often you're going back and forth between the same limits 2 times, 4 times, 6 times, a bunch of times, hence the word cyclic, but it doesn't have to be. If you just go twice, that would be cyclic voltammetry. You can go 3 times. You know, you could start here, you can go up, you can go down further than you started, you can end somewhere different. You know, these can all sort of be different levels. This would still be CV. It's defined only really LSV if you just go once, one direction, up or down, something like that. Okay, so that's LSV and CV. Now, SWV, which is the last one you talked about. Oh, see, I just said I'm going to do it here. I'm going to do it this time, I swear. SWV, that's square wave voltammetry. Wow, it is a lot easier. Thanks, Alex. So let's draw. Okay, so square wave voltammetry, forget about that. It's an interesting kind of technique. So I just showed you the waveform for potential and time for LSV and CV. It's just straight lines. Square wave, I'll explain it in a bit, I'll show you, but basically it's actually this kind of a pattern. So you see it's like staircases, except the top part is increasing and the bottom part is increasing. You could do this in a cyclic fashion where you then start going the other direction. There's sometimes people will say like cyclic square wave. You might see like something like that, like C square wave voltammetry. But you can just go one, or you could go sort of, if I were to draw, for example, like, let's use a better color than that. So if I were to draw, like, you can imagine this is almost like LSV or CV. I could sort of draw a line, and there's sort of like an effective scan rate about how fast I'm moving, but I have this, up and down kind of pattern that's going on. All right. I'll get into the analysis of these in just a minute here, but I wanted to kind of explain the waveforms because they're a bit interesting, right? So that is the waveform of square wave, and that's the difference between square wave and cyclic voltammetry, and cyclic voltammetry as a matter of waveform, let's say. Okay. Now let me share our website with you. And we have a knowledge base article on this, which is pretty useful. So I'm also going to link this. Let me try to link this into the chat for you. This is the article that I'm showing right here. So this is square wave voltammetry. So in short, square wave voltammetry is used to kind of get like a background subtracted cyclic voltammogram, something like that. Okay, so what it's doing is, you think of this as up-down kind of a thing, right? The other way to look at this is this forward pulse and then this reverse pulse. And so what you're doing is you're sweeping, you're sweeping, right? You're changing the potential, like from some point positively or negatively, but just positively in this example. You're sweeping the potential up, and you're measuring it. Now, you're doing the same thing with CV and LSV. You're sweeping the potential and you're measuring it progressively. But in this case, we sweep up and then we sweep back. And so this reverse pulse is allowing me to sort of get like a background, right? So in electrochemistry, we often have like Faradaic and non-Faradaic processes. We have like background processes. And so the square wave is basically allowing us to measure like it's still current, like the end result of a CV or an LSV, might be, right, you'll get current versus potential. And so for a CV, you get the predictable sort of this kind of behavior. Now with a square wave voltammeter, you'll get something similar, except the current is more like, it's more like a difference, right? Because you're sort of getting the upper minus the lower all the time. And so you typically clarify, sometimes you get a little more clear peaks, because what's not obvious that when you're doing LSV or CV is that you have a lot of background current that builds up. And so by doing square wave, you kind of subtract that. It allows you to hone in on the processes that you're after. Okay. And so actually, if you talk to some like very purist electrochemists, they'll express how cyclic voltammetry is actually much, much worse than square wave. And they have a point, and there's a brilliant researcher. I think it is Jane Oster-Young. I think that's the name. Apologies if it's not the right first name, but Oster-Young. I believe there's a series of pulse technique publications, and it might be referenced in here actually. So if I Oster-Young, yeah. So I think it's Jane Oster-Young. I think that's what it is. Maybe like it appears to be two. So anyway, there's the Oster-Young, or the Oster-Youngs, many years ago, published many of these papers on different pulse techniques, including square wave and differential pulse and things like that. So yeah, so here's the plot that I just sort of drew. You sort of clarify where the peaks are much more easily because you're subtracting the background constantly. It's a more sophisticated form of analysis. The downsides, if you will, to doing square wave as compared to cyclic voltammetry, and I will say that cyclic voltammetry has kind of won, right? Most people do CV. Most people don't do square wave. They don't really know what square wave as well as they know CV. CV has won the like sweepstakes of what are electrochemists actually going to do most of the time. but I still find square wave to be really powerful. The problem is it's just tricky. Square wave has more parameters, right? You have to pick a lot of different things. CV is easier in some sense. You pick where you start, you pick where you're going, and how fast you're getting there. Easy, right? It doesn't require as much like investigation per se. Whereas square wave has all these parameters, right? Amplitude, period. Okay, well, I'm gonna where's the plot here? So I'm gonna go up. I'm gonna hold that for some short period of time. Usually some milliseconds. I'm gonna go back down. I'm gonna go up, down. Well, how long should I do those things? How long should I wait? How far should I go up and down? Those aren't necessarily easy things to answer, and it requires more trial and error. And then, rightfully so, people will argue that, well, if you don't pick these parameters appropriately, how accurate is your data? And that's valid. So it's harder in some sense because of the different parameters you have to pick. But in my opinion, that shouldn't invalidate the technique. It just means that if you iterate on trial and error and get your values, you can get a lot of really useful and perhaps more clarified information doing square wave voltammetry than you can from doing cyclic voltammetry or linear sweep voltammetry by itself. So I hope that answers your question about those 3 techniques. Okay, so let's see. I'll move right along here, and I will try to give preference if I see questions from any of our members, just so you are aware. So the next question from Aswin is how to identify pitting potentials in the Tafel plot. Gosh, that's a good question. So, pitting potentials. So I assume that you're referring to, like a corrosion process. And so I'll just talk briefly about this because I don't know if I know the answer 100%, especially as it relates to how to find it in a Tafel plot specifically. But as it relates to corrosion processes, you're talking about, you have a surface. Probably shouldn't use blue because blue is usually liquid. Let's use right, here's my surface and here's my electrolyte. So this is my, electrode or whatever. And here's my light. So eventually when you're doing a corrosion experiment, at some point you sort of get this, it starts to degrade or something like that, right? And so this would be your, pit nucleation, pitting, nucleation point or whatever, and then it'll grow and maybe corrode into whatever. So at what potential that starts to happen? Well, I guess, let me think. So when you're doing a Tafel plot, you're getting something like potential versus like log of current or something like that, right? So in some sense, I guess what you're probably looking for is where you have some sort of a sharp change. So like, gosh, I'm gonna, if you have a Tafel plot that it's something like this, and please, heavily, I'll stress now that this is very vague in general, and Tafel plots vary for all sorts of different applications. People do all kinds of different analyses with Tafel plots, and it's kind of all over the place, I will say. For example, if you have a Tafel plot like this, you might take a slope here and say this is, 60 millivolts per decade, and that's giving me information about about the kinetic process, and then maybe this portion here is 120 millivolts, per decade. And so that gives me more information. So the best sort of general answer I could give, which is just, again, this is somewhat of an educated guess, if you will, I don't know how else to kind of put it, is that, you might give some example, like, well, if I have a Tafel plot, if I've done my Tafel transforms and I've got some sort of a inflection point or something like that, then there's there's some sort of radical change in the how would you say, in the magnitude of the change of current, something like that might be, like a critical potential. So like, this might be a potential that right here is, related to some sort of a shift in the kinetic behavior, which could be indicative of a pitting process. but that's like the best that I can do. I don't, again, it sort of depends specifically on the system, and I would have to probably see the data. But, when people are doing Tafel plots, oftentimes they are looking at like multiple different regions of it and like the slopes related to those regions over that, range of potentials or something like that. And so, in some form of analysis, you could say like that the transitory, parts between different parts, Tafel slope values might be an indication of a potential related to some process. But it's tricky too, because, when you're doing corrosion processes, it's not necessarily going to behave the way, you're doing CV and you get a peak. It's like, well, okay, well, that peak potential or whatever the E, 1/2, let's say, of a reversible process, as I'm drawing it with my finger here instead of the screen. So, okay, whatever, you have this CV, you take the, halfway between these two, your E 1/2. Well, that's an easy, like, that's the potential of interest or whatever. But pitting processes don't really behave this way for the most part. So like, this kind of analysis isn't as easy to do. So hopefully that's a decent answer for you. I know that's a little bit complicated. It's also a good question. It's pretty complicated question. All right, moving on here. Alex is watching and sending some delightful emojis to me, which is very nice. Okay, so Saurav, hi, thank you for joining us. Question: for the determination of electrochemically active surface area in capacitive method, it is difficult to get the value of specific capacitance. Do you have any source of values for different nanoparticles? So in capacitive method, I guess I'm not sure. I don't really know if you might have to clarify. I don't know what you mean by your determination of electrochemically active surface area in capacitive method. So I'm not 100% sure what you mean by capacitive method. Like, are you, if you're doing like CV or something like that of like a pure capacitor, sometimes you just go back and forth and you get this kind of pattern, and then you like increase the scan rate, and then you get sort of like an increasing like envelope or window or something like that as your scan rate increases, something like that. But to get the electrochemically active surface area, like I've talked about this before. I mean, I've talked about it with terms of platinum. One of the only real, well, one of the ways that I know best how, this is done is that you get this area here of your platinum, right? And that this area here, you relate to 210, again, I think it's microcoulombs per centimeter squared. It's micro or milli. I would for some reason forget this, but you can use this to monitor essentially what the electrochemically active surface area is, get a measure of it. But as far as the capacitive method is concerned, I guess I don't really know what that is. And then values for different nanopart. I mean, honestly, the answer to most of those kinds of questions, what other values are there or whatever, is basically you're going to have to search the literature most likely to find, if someone's using XYZ catalyst or nanoparticle or element. Hopefully someone has published on it before, because you'd have to look through the literature to find that. I don't have personally like some repository of different values of specific surface area or capacitances or anything like that. I guess the only other thing I'll say is that, in this case, you can get a measure of the capacitance from CV related to the scan rate and the current, basically. And again, that's another thing that I always mess up the equation, but the current is related to the scan rate and the capacitance, and you can do this through CV. And the other way is doing impedance. If you do some impedance, you can do a circuit fit, and you can fit like a Randall's element or something like that, right? And you can get a measure for this capacitor. So electrochemically, you can measure the value of a capacitor pretty easily. And then what I just mentioned about trying to figure out what the active surface area is through whichever method or tabulated data, then you can just get your specific capacitance. Okay, let's see. What is the next in line here? I see. So Salah says, can you explain the concept of choosing the suitable counter current and reference current? How does it influence the performance? I assume you mean electrode and not current. Suitable count. Oh yeah. Okay. So that's the next. Yeah. You clarified the next question. I see. The concept of choosing a suitable counter electrode and reference electrode, how does it influence the reaction results? Sure. So choosing a suitable counter electrode is of less consequence than choosing a suitable reference electrode. The counter electrode matters, but it does not matter as much as the reference electrode does when it comes to, are my results going to be good or absolutely terrible? Okay. We may have talked about this in the past. I know Alex has covered this as well. Generally speaking, you want your counter electrode surface area to be bigger than your working electrode. Okay. So you want the counter electrode surface area to working electrode surface area. You want that to be maybe 5:1 or 10:1. So just bigger, something large. And so very briefly, that's because of compliance voltage issues. In particular, of course, because you're asking about reference electrodes, you're doing a 3-electrode system. And so what you have is your working electrode. This is your working electrode. You have your counter electrode, and you have your reference electrode, right? In solution. Basically, you're really only concerned about what's going on here. You're doing whatever you're doing. You're doing your CV, you're doing your EIS, your square wave voltammetry, whatever you're doing, you're studying the reactions that are happening at this working electrode. Well, the potential is determined between these two, the reference and the working, but in reality, the current goes between counter. Wonder if use a different color for this, just so it's a little more clear. The current goes between these two, right? So you have a separate sort of a system here. And I'm not getting heavily into how a potentiostat works here, but basically the main point about the counter electrode is that it needs to be able to deliver the current in the form of electrons flowing either from or to the working electrode without any blockages, without any delay, without any limitations. And so one of the ways to do that is to simply have a very large surface area here. A large surface area, because electrochemistry is a surface science, means that it can generate a tremendous amount of current through one means or another, compared to the working electrode. Whereas if it's the other way around, if the counter electrode has a small surface area, it will have to work harder. Basically, the potentiostat will have to work harder to provide the current that is required at the working electrode. And if that's the case, that the potentiostat's going to have to increase the voltage a lot. It's going to potentially lead to problems in your solution, unwanted side products. So basically, the counter electrode just needs to be something that's very conductive, relatively inert, and something that can have a high enough surface area. So typically that's platinum, it's graphite. Sometimes if you're doing, other kinds of systems, it'll be like a mesh, some people have like a nickel mesh or I don't know, things like this, but basically just something that is a big surface area, large, exact shape and size doesn't always matter. And in most experiments, it doesn't usually matter. There are some cases where people prefer to not use platinum. Some of those reasons are that in aggressive situations over time, there's been some studies in the past, right, where some people have noted that platinum can migrate over periods of time from the counter electrode to the working electrode. And it's like, well, if you don't want to have platinum contamination, you want to avoid using platinum. And then there's other reasons why some people, it depends on if you're doing non-aqueous, you're doing aqueous. There's a lot of systems, right? And some systems are just not as compatible with certain metals, right? They might dissolve or they might be unstable, things like that, of course, right? So it can be highly system dependent. But that being said, platinum is probably just overall the most popular. Platinum is it's a noble metal. Of course it's expensive, but it works very, very nicely. It's very conductive, and it performs electrochemical reactions very, very easily. It's a very ideal counter electrode. But graphite, carbon, in various, a rod or plate or something like that. There's typically like a graphite rod is an easy counter electrode as well. That can be used. It's also a lot less expensive. But again, it just depends on the situation that is being tested in, if it's stable or it's going to dissolve or whatever. So these are the most common that are used, and mostly, like I said, the surface area is really the thing that matters the most. Now, the reference electrode is where it really does matter. So there's a lot of considerations with respect to the reference electrode. The first and most obvious one is that reference electrodes typically have something inside here. This is where the reference electrode, call it couple, basically what determines its potential. So this could be, right, silver chloride, could be calomel, which is mercury chloride. It could be mercury sulfate. These are some of the most popular ones. The alkaline one of choice is usually mercury oxide. Essentially, through the Nernst equation and the concentration of solvent and electrolyte in and around whatever this couple is, whatever this material is, the potential is set. And that's how the potentiostat is controlled. Now, it doesn't really matter what this potential is. So these have different standard potentials. This one's it's like 200 millivolts, something like that. Calomel it's like 220, something like that. Mercury sulfate is like 650. Mercury oxide's like 100. So they have different standard potentials, but it doesn't matter. It just means that if you're picking your CV potentials, let's say, you're going to start from 0 to 1. Well, now instead you're going to start at minus 200 to 800. You're just shifting it. It's all relative. It doesn't really matter what it is, just as long as you know what it is. So that part of it isn't important. What is important are more about the construction of the reference electrode. And this is why it has the potential, pun intended, I guess, to mess with your experiment badly. The first is the frit. So everything in the reference electrode is self-contained. Its potential and its stability requires that these things be sort of all together contained. And so that means there has to be a separation between the reference electrode and the main solution that it's sitting in. And that usually comes in the form of a frit. These can be ceramic frits, these can be glass frits, but they have to be porous. And so they allow communication. Sorry, that was messy looking. I want to draw this a little better. Basically, you have communication in and out, but it's very slow. Because if it doesn't communicate at all, then it doesn't work. But there has to be some sort of electronic communication, and it comes in the form of very slow diffusion of ions in and out. Now, the ways that this can mess with things badly, the first is that if the frit is blocked or it's bad or it's the pores are too small or something like this, if this is really, really slow, this will give you a very high impedance. All right. And that can make the experiment behave very poorly. It makes it hard on the potentiostat. It can mess up your data and cause it, especially if you're doing something fast like impedance. It can be very it'll only work for very slow experiments in some cases, or it still will behave poorly. The other is that because there's some diffusion in and out here, well, if you have silver chloride or calomel, for example, the supporting electrolyte in here is usually something like KCl or NaCl. All right, so this means that you have chloride ions inside here. Well, that means that necessarily, slowly, but still over some period of time, you might have chloride making its way into the main solution. Chloride is often undesirable, especially if you're doing like very, very sensitive electrochemistry. If you're not so concerned about it, it doesn't necessarily affect your experiment. But for people who are doing very sensitive kinds of tests, especially with things like platinum or palladium, chloride has this tendency to plug up active sites on platinum. So it's like you have your platinum, I don't know, you have your platinum electrode and it's, doing whatever reaction you're doing on it. Well, chloride has this tendency to like block it. It'll sort of clog the platinum. It reduces its electrocatalytic activity to some extent. And so it's like a lot of times you're trying to avoid platinum getting in the way at all. So you might use, something else. You might use a reference electrode that has, this is sulfate, right? Sulfate is less interfering. So those are some of the considerations as well. Frit, ions, and there's ways to get around this, like double junction and salt bridges. This conversation can go for a lot longer. I'm going to cut it off here. But basically, when it comes to the reference electrode, the main things you're trying to be concerned about are making sure it's in proper working order, making sure the frit is in good shape, making sure you've chosen a stable electrochemistry, like electrochemical couple, and making sure that the supporting electrolyte, the electrolyte, there's some compatibility. Often you'll try to pick a reference electrode with compatibility of the supporting electrolyte compared with your main electrolyte. So that if there's any crossover or contamination in either direction, you don't want to have it cross over into your reference electrode and make your reference electrode work more poorly. So that's hopefully a relatively brief overview of that question. So moving along here, I see Ali has asked, can you explain why the discharge capacity in the first cycle is high? Even some lithium ions are consumed in SEI later. Well, you've answered the question, Ali. I see you asked another. I'm just going to see here. If you use the same active material for anode for the lithium ion battery in the supercapacitor. Okay, I'll answer that second. This first one's a little bit. So this question might be over and above if you're not really familiar with batteries. But essentially your first charge discharge, if you're looking at capacity like milliamp hours in voltage, your first discharge might be out here, and then the rest of the charge discharge will be over here. So this is two things. The first is that it's basic, it's SEI. When you like build a battery from scratch and you do your first charge or your first discharge, basic first discharge usually, the SEI hasn't formed yet. And so the first discharge curve isn't real in some sense as it relates to the steady state function of the battery, because the SEI being formed takes energy. And then once the SEI is formed, mainly on the anode, is a little bit on the cathode too. Once it's formed, the battery settles into this sort of, if it's a good battery, right? Of course, there's if it's not behaving well, that's a different story. But if it's a well-made battery or whatever, it settles into this normal charge discharge kind of behavior. But the SEI is a decomposition layer that forms on the, it's a weird phenomenon as I understand it. It's basically decomposed electrolyte with some lithium ions and some lithium salts and some other decomposition products that forms a film on the anode that in and of itself acts as a barrier for preventing future decomposition of more electrolyte. And so it is in many ways necessary for the functional operation of a battery that SEI has to form. And so that first cycle, actually, I mean, what they do commercially, for example, like with your phone battery, right? With a laptop battery is when you get your phone or your battery or what, if fully charged or whatever for the first time, it's actually been charged and discharged 2 or 3 times in the factory, because they charge it up or they discharge it for whatever, state they put it together in. And they have to charge it a couple times to get the SEI layer formed, because this capacity right here is not, like, you wouldn't want your battery management system to assume that this right here is the expected capacity. Otherwise, your phone or whatever would always think your battery is at 50% state of charge, because this is whatever, halfway. No, in fact, this is 100% here. This is like just the initial SEI thing. You don't really consider it when it's related to the actual charge discharge capabilities of the battery. I will move to the next question in order here, and then I think, Ali, you had another question about supercapacitors. But first, Angel says, I have a question referring to LSV and oxygen reduction reaction. So I use a carbonaceous material on the electrode. I get the typical response, but I can't get the KL plot to be less than 6 electrodes. 6 electrons. Yeah. So first of all, carbonaceous materials aren't great at doing oxygen reduction. They're just not. That doesn't mean they can't, but they're not great at it. The other thing is that, I assume if you're doing a Koutecky-Levich plot, you're doing a rotating experiment. I guess there's a lot that I could possibly say about that. Let me pull up this. Hang on a sec. I have some slides. So when it comes to the Koutecky-Levich analysis, it might just require some trial and error. But for example, where you choose to take the it's supposed to be done in the transition region, if you will, right, between your diffusional controlled, which is just for Levich analysis, in the kinetic region. You want to get something in sort of in the middle here. So in many ways, you're looking for, basically, if you can find the continuous kind of analysis here, your Tafel, you might have to be how do I put this? Opportunistic, or what's the right word? Clever about the range of potential that you pick for your Koutecky-Levich analysis, because what you're saying is basically you're getting a Tafel slope of what, I guess 20 millivolts per decade, right? 120 millivolts per decade. I did this this is a webinar I did some time ago, right? So basically 120 millivolts per decade is a 1 electron irreversible process, a perfect, ideal sort of a thing. So in theory, if you're getting what, divided by 6 electrons, and you should be getting, you're telling me that you're basically measuring 20, I don't know, millivolts per decade, and that's too low. So, what you want to measure is 30 or something, right? 30 would be over 4. So, you might just have to adjust the potential of your Tafel, where you're measuring your Tafel slope. I don't have an example Tafel slope in this slide. I have it in my data somewhere. But in any case, where you might want to consider adjusting, like I said, where you're taking your Tafel slope, and this sort of a game, because you're like, well, is it accurate? I know what potentials I should pick, but in reality, you have that. And then the other thing, it's odd, I think, perhaps, that you're getting more electrons than fewer electrons, because, as I said, carbon isn't really a great oxygen reduction catalyst by itself. But it might just require trial and error, in particular, as I said, where you're taking your Tafel slope, and then, backing up and making sure all the other sorts of parts of your experiment are operating properly, that your curves actually are good, your limits, your sweep rates. You could try slowing down your sweep rate. If you're sweeping too fast, maybe that's contributing. There's some of these trial and error of your experimental parameters that might help clarify the data too. Okay, so this was from Ali again. It looked like a second question related to the battery thing, but if you use the same material for anode in a lithium-ion battery and a supercapacitor. So for the supercapacitor, why same element oxidize and reduce at different potentials compared with lithium ion? So first of all, the potential that something will oxidize or reduce will be electrolyte dependent, like pH dependent and all that kind of stuff. So first of all, the media that you're using are probably wildly different. And then the second thing is, and again, without knowing more specifics about the systems exactly you're testing, in a battery in particular, for example, your potentials are versus lithium plus, like the potentials are different in the sense that they're reported with respect to a different reference. So that could be part of it. And then, like a battery is usually a 2-electrode system. And so it's not, it's not like an absolute potential, like it's a voltage. It's between two moving parts, right? Like anode and cathode use. So in a supercapacitor, maybe it's 2-electrode, but sometimes it's a 3-electrode. And so the difference in the potentials that you're talking about might just have something to do with the fact that the systems are in different media, different electrolyte, and the different reference points for each. So and that, and the processes might be different as well. Especially on a supercapacitor, the process for your lithium-ion battery, for example, like if you're doing a carbon material, is that it's intercalating lithium. It's a different process than for a supercapacitor. There's no Faradaic process. A battery is doing a Faradaic process, than a supercapacitor is typically not. So, entirely different processes. They would, in theory, have different potentials that they're going to have as well. So that would probably explain a difference too. All right, so next I think I see Mat Byung has said, when we perform charge discharge. Oh no, I think I already answered that one. Why is, oh no, it's just a similar question to before, is it? Or did I already answer it? Yeah, there was a similar question before, so I will read this one. Charge discharge, the first cycle is always larger, subsequent. Okay, so I actually happened to answer this question. If you didn't, yeah, okay. So Ali asked previously what the first one about SEI. Basically, the answer to your question is that the SEI is formed. So the SEI is formed on the first discharge or charge, sequence. That's the solid electrolyte interface, and it's basically a decomposition of your electrolyte that helps protect it to do the charge discharge. And so once the SEI is formed, unless it breaks down or unless it thickens over time, which that can happen, in the absence of other sorts of processes, the SEI formation is the reason for why your first one is bigger than the subsequent ones. And let's see, the second question here from Mat Byung is, in EIS, why do we need to scan for different frequencies? And why do the charge transfer resistance occurs in the low frequency region? Okay, so scanning different frequencies is because that's sort of the whole point, right? The whole point of impedance is that you're casting your process in the frequency domain rather than the time domain, because otherwise everything we're doing is in the time domain. We're doing electrochemistry in real time. So by choosing different frequencies, we can see how things that happen quickly versus things that happen slowly. So this one here, share with you. So this is from my impedance webinar, but you can see, when I talked about this in the beginning of my impedance webinar, basically like fast processes and slow processes, by scanning through different frequencies, you can look at one or the other. You can look at, different processes that are happening, different speeds. If you don't change your frequency, you might as well just be doing DC electrochemistry. So fundamentally, that's why you're doing EIS, is to look at things at different frequencies. And then charge transfer occurring in low frequency. Well, that's not entirely accurate. Charge transfer, charge transfer resistance, for example, if you're looking at like a Randall's element, let me try to get my second webinar here. So your Randall's element, for example, where you have your charge transfer resistance, you're getting the charge transfer resistance in some manner of thinking, like in this plot right here, like this is high frequency, right? Like this is low frequency. So if what you're thinking is that like, well, this is my like charge transfer resistance. Well, yeah, but you're still measuring it throughout all of the frequency. Like it's part of the graph. It's just that you get a like clarification of the exact magnitude by looking at the width of this semicircle, which happens to complete at low frequencies. But like it's all part of it. You're measuring the charge transfer resistance throughout. Like it's collectively all part of the experiment. It's not like you're only measuring it at low frequency. That's not really like the best way to think about it. It's being measured actively, like all throughout. It's just that by getting the width of the semicircle, you can get a measure of this RCT, this resistor value here. So I hope that's kind of clear. It's a bit of a odd way to think about it. It's not really accurate to say, for example, that like only at low frequency is where the charge transfer resistance is like showing up. It's all part of this, it's just that the value of it is seen and visualized through the width of the semicircle. Something like that, if that makes sense. Okay, Jesse says, as a follow-up to Matbiang's question, why are or would ion blocking electrodes be used in an EIS experiment? For example, measuring ionic resistance of a solid state electrolyte. Yeah, so blocking electrodes are a pretty cool concept. You do that for a couple of reasons. One is to get information about other parts of your system, like, for example, the membrane, the electrolyte, conductivity, things like that. Because, you use blocking electrodes. So you might use, so my wheelhouse is usually batteries. So I can use that as sort of an example, but get a good color here to draw. So like if you have a battery electrodes, you have your anode and your cathode, and you have charging and discharging going on. Am I sharing it right? I think I am. Okay. And charging and discharging going on, you've got like lithium ions either intercalating into here or intercalating into here. You have it's a Faradaic processes, whatever. Okay, well, if instead of that, you have blocking electrodes and you just have this like metal, like identical metals on both sides, or something like another way that blocking conditions are met is that you have your anode and cathode, but instead of a lithium salt, you use like another electrolyte that doesn't have lithium ion. So basically, like there's no Faradaic process that can happen. And so again, what you're doing then is that all the electrochemistry or the impedance or whatever the results you're getting are not really related to the Faradaic process that's happening, because otherwise which is what you're usually trying to do. You're trying to measure the charge discharge capabilities. You're trying to measure the Faradaic process, right? A battery is a Faradaic process of charging and discharging. But if you're trying to study the other things like the membrane, right, or the conductivity, it's usually sigma, either through the membrane or the conductivity of my electrolyte or whatever, something else, well, you can take the Faradaic process out of the equation, either by using, like I said, no lithium salt, or if it's a fuel cell, something similar, like no like Faradaic salt or process that will help run, or you use an electrode, like people put like metal or whatever. So it's blocking. So it's like solid, right? It won't intercalate anything. So that's one reason. And then the other reason that people do is to measure things like the porosity or the tortuosity or stuff like this. So there's this, I did another webinar, like an advanced fitting webinar on this concept of called tortuosity, basically looking at a blocking condition. So an electrode was used with some, I think this was the case, was they used like no salt, right? But the electrode had some pores in it, right? So this is not the same as this. This would be like holes or like pores or something, had some sort of porous microstructure or something like that, nanotubes or whatever. And so when you do blocking conditions, you make sure there's no Faradaic processes that are occurring. Another application of this is that you're measuring like on a microscopic level, there's some microstructure of my electrode, right? So if I like zoom in here, right? Well, I'm measuring like the transport of these pores, or I'm measuring the capacitance of this system, right, as the electrolyte penetrates the pores. And so I can get a measure of tortuosity is one, I think it's tau. And basically it's a measure of like the path length compared to a perfect straight line. So or the porosity, the pore structure, stuff like that. So without getting more specific again, because that would require more of like a literature study and just more of a complicated forum. But those are some of the applications, I guess, to answer your question again about why you do blocking conditions. It's to study sort of other things that are separate from the Faradaic process. That's the main crux of the system under study most of the time. Okay, so I see the next question by Tarek Keegan says, in electrochemical reduction experiments, how do we choose the applied potentials to drive the reaction to undergo, for example, experiments like nitrate N2 reduction to ammonia? It's a good question. I actually don't know a lot about like ammonia production. I think actually one of our colleagues did some of this in his PhD study. So it's a shame that he's not here because he'd probably answer this a lot better than I will. It depends, I guess I would say. So if let's just say your goal is to study, what would you say? Like, okay, I made some catalyst to do my, ammonia production, like nitrate reduction to ammonia, right? And I want to like measure its selectivity or its efficiency or something like that. Well, the shortest answer I would say is you want to pick a potential. So if I'm doing like, let's just draw like a CV, right? Like if this is a reduction, I'm doing UPAC convention here. So whether, maybe it makes a peak, like a reduction peak, or maybe it like just kind of starts decreasing. And so wherever you might sort of say like, like this region here, yellow's a terrible color. It's hard to see. Where the current starts to increase basically, or decrease for reduction, that would be like, well, that potential is the potential, again, for either case, whatever the situation may be. You might say like, whatever this potential is, I need to be at least here or slightly more negative. Yeah, Tim did some ammonia work, but the potential for a redox would be based on the thermodynamic process. Yeah. So I think Tim did, he did some like enzyme stuff too, which is a little bit different, if I'm not mistaken, but I'm not sure. Anyway, our colleague Tim, if you know Tim, if you've met him, he knows more about this than me. And anyway, whatever that potential is, basically, as long as you're more negative than it, you're doing the right. You're increasing the overpotential, right? Your overpotential is basically this. If this is the E0 or the whatever the reaction is, the potential for that process, that ammonia, your overpotential is E minus E0, and so having a sufficient overpotential is the driving force, right? And so having a large enough overpotential drives the reaction. Now, how far or how big that should be, well, that's where it really depends, to be honest. Because if you just pick okay, well, if this is like 500 millivolts, well, if I'm anywhere negative of this, I'm doing my reduction. So if I just pick 400 millivolts, I have 100 millivolts of overpotential, right? And I'm going to do my experiment. But maybe that's not enough. I want to really drive the reaction. Okay, well, what if I just pick like minus 500 and I have a full volt? Well, in some sense, that's really good. I have a high driving force. But on another sense, you can run into problems. For example, if I go too negative, if this is an aqueous system, I'm going to start evolving hydrogen. Well, now maybe my current is related to ammonia production and hydrogen production. Well, I don't want that. I want to try and dedicate as much of the current that I'm, getting, or as much of the product that I'm measuring to the process of interest, which, in my case is ammonia production. So I want to try to make sure that my electrochemistry is as isolated as possible. Now, that's impossible to fully isolate your electrochemistry to one thing. I mean, it's not basically possible, right? Even with nothing else really present, you're still going to have double layer capacitance, and you'll have charge buildup, and you might have other sorts of side reactions happen. It's going to be some amount of interference of other stuff, I guess. But the first answer is to basically have just enough of an overpotential to drive the reaction to produce ammonia at all, which means it has to be a decent overpotential. Now, a rule of if you have a peak, you might pick somewhere just beyond where the peak is, or right at the peak potential, something like that. That is a guarantee that I'm driving the reaction with some degree of efficiency. But the other answer that I could give that question is really related to the literature, for example, that if you look at, if you're trying to compare with some papers or some colleagues or contemporaries about what they've reported, it is pretty important to try and compare with what they chose. So they might say, well, we got, 30% selectivity or efficiency, and this, current density at, Y volts or whatever. So whatever the literature, they might, because this will change, right? If you could just increase the potential indefinitely, or your overpotential, well, then you're not playing the same game as everybody else, right? Then you're not comparing apples to apples, so to speak. So what you want to do is try and make sure not only that you have a potential where you're driving the reaction, but that you're not so far that other side reactions are happening, and also that it's comparable to what others have done in the literature, so that you can be sure as much as possible that the reaction that you are driving is in line with what others have done as well. Okay, next I see Bia has asked, can you please explain the role of electrolyte in battery other than transport of ions? Other than transport of ions. I mean, and that is basically the point of the electrolyte in a battery. Otherwise, its point is to connect, the same purpose that electrolyte has in every other electrochemistry experiment, which is to complete the circuit. Every electrochemistry experiment in some fashion, whether it has a reference electrode or not, now in this case we're not, is that we have two electrodes connected to each other through some device, right? What's the symbol? It's some sort of thing, right? We have currents or, that can flow between the two. Well, that can't happen indefinitely. There has to be a connection, basically charge balance, charge neutrality going on. Otherwise, it's not physically possible. So, the electrolyte between a battery is the same as the electrolyte in a Faraday cell or a rotating disk electrode experiment. It's the same thing, that you have to have some, electrons moving to connect everything. And so in the cabling in your potentiostat connecting your electrodes, that takes place of electricity. It's actual flow of electrons right through wires. But in the electrolyte, it's the flow of ions. It's chloride ions moving in one direction, or sodium ions moving in the other direction. Whether there's negatives moving to the left or positives moving to the right, whatever, you have charge balance, you have movement of charge. And so that's mainly the purpose, right? I mean, in addition to, as you said, in a battery, right? Well, actually, that's what you said, is transport of ions. It's connecting. The other, I guess I'll say for a battery, since you asked for a battery, the other purpose, specifically like for a sodium ion or a lithium ion battery, is to supply those ions. So you can imagine that in a battery electrode, here's my anode and here's my cathode. Okay. When it's charging, lithium ions are basically leaving the cathode and they're going into the anode during charge. And during discharge, it's the opposite. So during discharge, lithium goes from the anode to the cathode. Okay. So the other purpose that the electrolyte does is it facilitates this. So the way I've drawn this looks, in reality, it's like you have a coin cell or a cylindrical cell. These are really close. They're like smushed together. But compared to the size of an ion, this distance is quite large. And so what you actually have, like microscopically, is this like chain of lithium ions, like all holding hands in a big row. And so what actually happens is like a lithium ion moves here and it just pushes all of these over a little. And so the one on the end is what goes in. And so you have like a continuous connection in a tray. This is really what's happening in solution in all electrochemistry, is that you have a chain of ions that's connecting a thing. And so you don't have to wait for an individual ion to like slowly move its way a seemingly infinite distance from one electrode to the other. And so that's true of batteries and of anything else, but really it's charge neutrality and providing that sort of connection. And then in lithium ion battery particular, in batteries, it's providing a source of the ion for intercalation, deintercalation, which is part of the charge discharge process. Okay, so for KOH electrolyte, what supporting electrolyte should we choose? It is the supporting electrolyte. KOH is like, this isn't like non-aqueous where you have like acetonitrile and like ferrocene, and then you need like TBA-PF6. It's sort of like there's like multiple things here. If you have like 0.1 molar KOH, you don't need another thing in there. That is, it's supporting electrolyte. You don't need anything else. Okay, so there's a follow-up from Bia about the ion. So thanks, but can electrolyte be used as dielectric, like in capacitors, to increase the storage capacity of ions? So an electrolyte is a dielectric material. I guess I don't, like in a capacitor, to increase the storage capacity of ions. I'm not sure I know the answer to that question. Like in a capacitor, the electrolyte in between is a dielectric. So like the answer is yes in that sense. It is a dielectric. Like everything, even air has a dielectric constant. It's a very poor dielectric, but it is one. Right. And so in a capacitor, I guess I don't understand how it relates to this. Like, I don't know what storage capacity of ions exactly means. But as far as the dielectric properties are concerned, like that is what an electrolyte is functioning as for sure. So I think some answer to your question is yes. I don't know 100% how to answer the idea of storage capacity of ions though. So you can either clarify or at least, I'm not sure how much more I can say to that. Ion says, if I want to do homogeneous molecular electrocatalysis with non-aqueous reference electrode, how much water can I use maximum? That's a good question. That really also probably depends more on your system. So a lot of non-aqueous systems are very water sensitive. And so the answer is probably almost none. It probably depends on like how hygroscopic, right? That's the property of how much something absorbs water, your electrodes or your electrolyte is. So like, for example, if you're doing something like a ionic liquids are extremely hygroscopic. So you don't want to have them exposed to almost any water at all. They have to be used almost exclusively in a glove box or a sealed cell or something like that. Other solvents, like, I don't know, I don't have the most experience with non-aqueous electrochemistry, so pardon if there's if this isn't perfectly accurate, but like, you might use like acetonitrile with a thing and you could just use it out in the open, like in a hood or something, but like you don't have to be in a glove box because it can tolerate some small amounts of water that might be in the air. It won't be as big of a deal. So I guess the real answer is that it depends on your system, right? But perhaps the way I would put it here is that, conventional wisdom might suggest that like you want to avoid water at all costs. And to some extent, that's true. If you're doing non-aqueous electrochemistry, you don't want to just douse it with water, of course, if you're trying to avoid that. But some systems are much more tolerant of a little bit of water than others. And so it really just depends on what you're doing. Whether if you're doing like a heavy reduction or something like that, water has a narrower potential window, than acetonitrile or DMSO or something like that. So you'll start to, like, you would start to see like a peak, before you would expect to see one if you have too much water. For example, like maybe you'll start seeing a reduction of water or an oxidation of water, at 1 volt or -1 volt, and the electrolyte survives until 2 or -2. Okay. That's only a problem if that peak, like, I don't know, overlaps or something with a process that you're trying to study. Because otherwise it's like, again, this is why I say it's like tolerant. You can be a little tolerant of it, because it's like, if you're studying some process and there's an extra bit of water stuff happening, but it's nowhere near what you're studying, well, then maybe it doesn't matter so much. But again, it's going to depend. It's going to depend on your system. Sadaf says people used AG silver wire as a pseudo reference electrode. What does it mean? Can we use AG wire as reference in any electrolyte? So yes, but it's not the best idea. So you can, and the reason that they use that silver wire is used is because I'm going to pull up another article on our website here. And I use this to talk about it just a little bit. So we have this non-aqueous reference electrode article on our knowledge base. I will also link this in the chat if you want to take a look at this on your own time as well. So there's the link to the article that I'm showing right now. The silver wire works as a pseudo reference because it's not, so you'll have like, let's see, I don't know if it shows, if I have it just sort of a simply the equation shown in this article. Yeah, this article kind of goes into more details of other non-aqueous couples, not just the pseudo reference. So the silver wire acts as a pseudo reference electrode because its reaction is basically, Ag plus an electron goes to Ag. And this is not as controllable as a reference couple. If you just dip a silver wire and it's not contained with an electrolyte, and most redox couples, like the ones I talked about before, like silver chloride or calomel or whatever, these are aqueous redox couples. And so when you're doing non-aqueous, you often have to use a pseudo reference or an internal reference or something like that, because it can actually work, but it's not generally advisable to mix aqueous and non-aqueous. Again, I just talked about whether something can tolerate water or not. That's a whole thing too. But the point is that when you're working in a non-aqueous system, you generally want to avoid having aqueous things. And so basically, because of the simple fact that most reference couples are aqueous, you sort of get into this situation of using a silver wire by itself. You have to have some reference. Some people use also like steel, like hastelloy. There's a variety of metals, and they're relatively non-polarizable, which means that they don't change their potential too much, but they're not as not as stable as a full reference electrode that is basically governed by the Nernst equation, where that potential is really firmly fixed. Okay, and this article goes into some options where you can take the silver wire and you can do stuff like fill it with silver nitrate and make a silver nitrate couple. Now it just kind of happens that the non-aqueous couples like silver nitrate and these ones are a little bit less stable than the aqueous ones. So it's kind of one of the struggles of non-aqueous electrochemistry in general. Now, to your question about can you use it in any electrolyte, you can, but it's like, for the most part, unless you have some sort of strange or unique or severe limitations of your aqueous setup, there's really no need to use a silver wire. You should use a real reference couple because you'll have much better control. Because otherwise you have something like this where it's drifting. This is like measurement of the pseudo reference electrode here, moving. You might have something like, it's like if this is your reference, well, it means that your potential that you're measuring over your cyclic voltammetry or your bulk electrolysis, whatever you're doing, is moving 20, 30, 40, 50 millivolts over time. That's not ideal. You don't want to have it be doing that. I mean, it's better than nothing, but it's certainly not ideal if it drifts a lot. The surface state of your silver wire is there's some oxidation, and it's less stable than a reference couple. So if you're in aqueous system, you don't really want to be forcing yourself to use something that isn't well controlled, like a real aqueous reference couple. It looks like, Bia, you were asking more about this dielectric. And Alex, I think you said, let me just sort of read through this discussion here. So the electrolyte as a dielectric is to a degree. The electrical double layer in and of itself is a capacitor, right? Exactly. Lithium ions at anode in a lithium ion battery, how the electrolyte is a dielectric. So, that I don't know. Let's see for a second here. I mean, so I just don't know if like, so like looking at the definition of dielectric, right? Like having the property of transmitting like without insulating, like when it comes to, I'm just trying to relate this. That's why I'm looking this up, just relating this to a battery. I think the first thing is just to differentiate between conductivity of ions and conductivity of electrolyte of electricity, basically. So like in some ways the electrolyte is always a dielectric because it's conducting right. When I drew that I drew before, like, oh well, you have charge moving this way through your potentiostat or whatever, and you have charge moving through electrolyte. This is the dielectric part. This is the it's insulating because, like, if you put two pieces of metal in a solution, right, and you connect them to like a potentiostat, you won't get this zap spark to go between them. That's like pure electricity, right? That doesn't happen. Now it conducts electricity because of ions flowing, but again, that's a difference. You're talking about the difference between current, electricity flowing, and ionic flow. And so whether the same sort of thing applies here, like whether it's a battery or it's a regular electrochemical system, the electrolyte is acting as this, it's insulating electrically, but it's conducting a chloride ion or a lithium ion that is moving charge, right? A chloride ion, a physical chloride ion that has a negative charge that is moving in this direction is in some ways the same as an electron that's moving through this wire. It's charge that's moving spatially, but they're different processes, right? This is like electrical conductivity, and this is ionic conductivity. And so the dielectric material is insulating in the perspective that it's not electrically conducting, but it's still moving charge in that way. I hope that is somewhat of a sufficient answer to what you're sort of talking about here. I think Ion has clarified with respect to the amount of water that can be used. Sometimes I need to add water as a proton source for electrocatalytic CO2 reduction reaction. Oh, yeah, that makes sense. I think there are other proton sources, but of course, water is a pretty good one. So it's sometimes hard to understand if reducing water or actually the catalytic process is going on. Yeah, that's a good point. I have not. I did some like alkaline electrochemistry involving CO2 processes, but like I was actually working on like the other half of the cell. It wasn't the reduction side. I was working on like anodes and oxidation stuff, and I didn't do a lot with non-aqueous, as I said. I did battery stuff, but I didn't do that. So I think that's tricky. I think that's a really good question. It is hard to tell, probably. I wonder if there's other like proton sources other than water that you could try to use if water is sort of complicating things there for you. Or you'll have to do some kinds of, say, like, how would you say, like trial and error, like background subtractive sorts of things, like do one without CO2, one with CO2, one with and without water, to see the effects of what the water addition does, in the presence or absence, to try and isolate whether or not what you hope, I guess, is happening is really actually happening. So something like that. But that's a really good thought. And, I think probably what you're looking at with your experiment is ultimately a good thing, in the sense that you're not you are quite tolerant of water if you are trying to use it for a purpose, to provide like a proton source for your reduction. So that might hopefully be helpful. You don't have to worry and be too stringent about it, I guess. Afreen says, can you please explain at which potential we should take impedance? Yeah, I get this question from time to time. I think I've been trying to think through why this is such a hot question, I guess. I get this question a lot when I do, brief diversion here. You can use specific weak acids with different pKa's in a non-aqueous system to look at CO2. Yeah, okay, yeah. So Alex is confirming. I did, he probably knows more about this than I do, so it's blame Alex. He's not here with me right now. Yeah, as I suspected, there's some other things you can add. Yeah, like maybe like acetic acid or something like that as a proton source if you want to try to avoid water. You're not really sure perhaps what the electrochemistry is doing on your water. So listen to Alex. As far as it relates to the potential to take EIS, again, I guess I'm always wondering where this question comes from. I haven't quite figured it out yet, but the answer is really quite simple. You're taking impedance at where you want to, whatever you're trying to study. If you just take impedance at open circuit potential, whatever is happening at open circuit potential is what you're studying. Like it's the same, impedance is the same as any other electrochemistry experiment. If you're gonna do bulk electrolysis, if you're gonna do chronoamperometry, chronopotentiometry, any of those kinds of things, you got to pick a potential that is generating the response at what you're trying to study. So like the previous question was about ammonia reduction. So I talked about the overpotential for your ammonia reduction, right? So you're going to pick some potential that's beyond that peak or something like that, right? And so you're going to be measuring your current response. Well, if you're trying to study the impedance of your ammonia reduction, well, the same logic applies. I can pick some potential where my peak is on the top of the peak or the other side of the peak, and then I'm studying whatever's going on there. I'm trying to study. So if I take open circuit potential in comparison, well, maybe at open circuit potential, I'm not reducing nitrate to ammonia or oxygen or whatever. So my open circuit potential is often where nothing of Faradaic interest is occurring. So if I can do my EIS at open circuit potential, and then I'm getting information that's happening on my electrodes only at open circuit, which is probably simple stuff like double layer capacitance and IR compensation, IR drop or whatever. If you're trying to study a Faradaic process, you're going to have to pick a potential that is where that process is occurring. So, and it's perfectly acceptable to choose multiple different potentials and do impedance at each of those potentials. And then, you're getting a sort of continuous result of impedance results, as a function of potential or something like that. But there is no one answer to that question, I guess, is sort of one of the points. Ranjit says, what is the relation between oxidation and reduction peaks with lithium or sodium in batteries? So the tricky thing is that when it comes to like redox peaks with like lithium or sodium ion batteries, you're not really often doing cyclic voltammetry with these systems. So there's a lot of ways to answer this. So I mean, when you're doing like a lithium ion battery, the peaks that you get will be related to whatever the material you're using is, like whatever the anode or cathode that you're studying is. And so sometimes those processes are intercalation, deintercalation. Sometimes they're a decomposition reaction. Sometimes it's like what's the other one? There's anyway, there's 2 or 3 different processes. It's been a while since I was in graduate school, so I can't pull this up quite as quickly, I guess. But anyway, the different processes that are that like carbon or like transition metal oxides or silicon, all sorts of different materials that make like anode or cathode materials for batteries will have that charge discharge reaction slightly differently. And so the peak position or the peaks that you might get will be probably, will be related to those. But as I said, the most common mode of operation is galvanostatic charging and discharging. So, when people think of peaks, and when I see people ask about peaks, my assumption is you're referring to cyclic voltammetry. If you're in that, it's just not something that's done quite as often. You have to scan quite slowly when you do cyclic voltammetry on batteries. And so it's the relation between them is whatever the type of charge discharge process is going on. It's going to define how many peaks there are and where they are, basically, just like almost any other electrochemical reaction. So I think our email here, I'll type our email in the chat here for you. If you want to send us an email, you can at pinewire@pineresearch.com if you have some more questions there that you wanted to follow up on. You can also, as I said at the outset, you can make a comment on this video. This, of course, if you're watching live, thank you for joining me. But if you are watching this after the fact, it will be, this is a video on our YouTube channel. So if you have a question that you want to ask, you can make a comment on the video, and that we'll be able to see it that way. And this is an event that, we are trying to run on a weekly basis at this time and this time slot on Fridays here. As I said, it's pretty self-explanatory. Ask us anything about electrochemistry, sort of an office hours feel. So I appreciate everybody who's joined this week. I'm going to probably wrap it up here. I don't see any other. I think I've answered everything that was asked here so far. So thank you all very much. I really appreciate the questions. I appreciate the engagement here. I hope that this was useful for everybody, and I will see everybody, I guess, next week. I hope everybody has a great weekend, and take care.